What is equivalent? We're still looking at equivalent fractions. This time we're going to use the linear model. Let's first review what is equivalent. Equivalent is similar to the word equal. Here's the equal sign. We know we've seen these in equations where we'll have something on one side and something on the other. When we see this symbol, we should read it as same as. So what's ever on one side of the equal sign has the same value and meaning as what's on the other. So no matter what I put on this side, whether I say 2 plus 2 equals, I can put 4 on this side because 2 plus 2 is the same as 4, or I can say 2 plus 2 equals 5 minus 1. Both of those expressions equals 4. So whatever I put here has to have the same value of what's on this side. They may look different, but it just means they are the same value. So when we think of equivalent fractions, it works the same way. Equivalent fractions are two fractions that have the same value. They may not look alike, but they have the same value. Two fractions that take up the same amount of space. So with that area model, if they are taking up that same amount of space, they are equivalent. Two fractions that represent the same distance. That means they are the same. They may not look alike, but if they go the same distance, they are equivalent. And that's what we're going to look at today, that linear model of going the same distance. So linear, remember it has that small word line in it. So we think of like a distance or a measurement. Because when we think of linear, we think of a ruler. And that means we are measuring either a length or a distance. So if you look at this ruler here, it's blown up. We're going to look at these right here, and this is in your metric system. So you have your centimeters, and in the between the centimeters, between the whole numbers, you have millimeters, those tiny little spaces where they still have value. They are still covering a distance. So we're going to focus in on these small pieces, which are the fractions. So there are 10 spaces between the 0 and the 1. But if we only go to this big tall line, we could say we are halfway between the 0 and the 1, which means we would mark that as 1/2. Or if we counted the spaces, that means we went over 5 out of the 10 spaces. So we broke this into tenths. So this would be 5/10. Or if we just look at here's one section, here's one section, we see that as the same as 1/2. So again, same amount of distance. It just is going to look a little different. So let's look at why that is. So let's pretend this is our ruler. Over here is 0. I'm going to get a pen so you can follow along with my thinking. If this is 0 and this is 1, then here is that complete distance. Just like what we just saw, that bigger line, we could say if we went from here to that bigger line on the ruler, we went 1/2, and then this other piece is 1/2. Or if you remember, there was actually 10 little spaces. If we came all the way down and we went down to where that line is right here, 1, 2, 3, 4, 5, and we're counting tenths, that would be 5/10 over. From here to here, same amount of distance. We just partitioned it differently. Still 0 to 1, we partitioned it differently. What if we partitioned it into 4? Notice that I'm going straight down. Again, I'm sure you would draw a much better line than I am. I'm still in the exact spot that I partitioned my whole, to where if it was in 2 pieces, from here to this line is 1/2. If I partitioned it into 4 pieces, from here to this line, that is 1/4, 2/4. If I partitioned it into 6 pieces, still on this line, that would be 1, 2, 3/6. Same amount of distance. I just partitioned it differently. What if I partitioned it into 8 pieces? Well, 1, 2, 3, 4/8 gets me the same amount of distance. If I did tenths, 1/10, 2/10, 3/10, 4/10, 5/10, same amount of distance. I can even divide it into 12ths. 1/12, 2/12, 3/12, 4/12, 5/12, 6/12 takes me to this line. Same amount of distance. I just partitioned my entire distance differently each time. That is equivalent fractions. Same distance, just partitioned differently. So we know that 1/2 is equivalent to 2/4. Numerically, they look different, but the value is the same. I can now say that these 2 pieces here in my fourths is equivalent to the same distance in the sixth if I said 3/6. I could also say all these fractions are equivalent, because I can rewrite 3/6 and say, you know what? It is equivalent to right here, which is my 4/8. Because these may look different when I write them as numbers, but the value and the distance is the same, because I'm still talking about the exact same amount of space, the same exact amount of distance. I just partitioned it differently. So let's look what this looks like on a true number line, a linear model for sure. So first up here, 0 to 1. Do you see how each of these, I'm looking at the exact same distance between 0 and 1. Each line is just partitioned differently. So let me get my line and I'm going to show you here. Wrong line. Let me get, there it is. So here's 1/2. Here's another. It takes 2 halves to go from 0 to 1. Each of these is a half. So 1/2. This is 1/2. But if I'm counting them from 0 to 1, it would be 1/2, 2 halves. I'm going to jump down here to my fourths. Now to do fourths, they're called fourths because it takes 4 to make it from 0 to 1. Okay, so here, 1/4, 2/4, 3/4, 4/4 to go from 0 to 1. How many fourths does it take to go to the halfway mark? So we want, again, that same distance. So I'm going to drag this up here. Here's 1/4. And look, I already made it to that halfway point. So 1/4, 2/4 is the same as 1/2. From 0 to a half, same amount of distance. I just partitioned it differently. So 1/2 is equivalent to 2/4. I'm going to move these out of the way. And now let's, not that one. There we go. So now I'm going to look at my thirds. So here's 1/3. Here is my 2/3. And here is my 3/3. To go from 0 to 1, it takes 3/3, because I partitioned that distance into 3 pieces, to 3 segments, 3/3 to go from 0 to 1. So let's look down here. This time I partitioned it into 6. Do you see how there's 6 sections? Same distance, I just partitioned it differently. So it takes 1, 2, 3, 4, 5, and I did not, there we go, 6. So it takes 6 of these pieces to go from 0 to 1. But I want to find an equivalent. So if I bring down a third, you can see that it takes 2 of the 1/6 pieces to equal 1/3, which means 1/3 is equivalent to 2/6. So we now have some equivalents that we have learned. We know that our 1/2 was the same as 2/4. And let me show you that one again. So let me bring up my fourths so you can see that. It went the same distance. And then down here was my 1/3 strip, and it covered the same amount of distance as our 2/6, because here it is right here. So let me write that to the side, that we now know that 1/3 is equivalent to 2/6. So again, with equivalent fractions, you're talking about the same whole, in this case, the same amount of distance, and all you're doing is partitioning it differently to find 2 fractions that talk about the same amount of space. Numerically, they may look differently, but the value, the distance, is the same. For example, 1/2 is the same as 2/4. We can also bring up our thirds and find out, our sixth, that 3/6 is the same as 1/2, and it's the same as 2/4. Because if you look, move this out of the way, see the line half goes straight down, the same amount of distance, 1/2, 2/4, 3/6. It covers the same amount of distance. You just partitioned your line differently. See if you can take a distance and cut it up, partition it different ways to find equivalent fractions with a linear model.